Alrighty, so let's get started. Right, so this used to be the Neptune Triton System Seminar Series, but we've actually recently sort of revamped our name to the Ice Giant System Seminar Series. And the reason for this was just sort of based on some recommendations from the decadal survey that came out in the last few weeks. We always, sort of, I'm gonna go ahead and mute folks and feel free to unmute yourself at any time. But so we sort of made this switch, analog objects to Neptune and Triton were obviously always welcome, but sort of by broadening our scope, our name to ice giant systems, we're sort of broadening our reach. And for the most part, the types of talks that you see here won't be any different, but we just kind of wanted to make sure that we were a little bit more inclusive of all of the systems that need some recognition. So this is now formally the Ice Giant System Seminar Series, and many of you may have noticed that the registration process for this seminar series has changed. So we used to have registration closing about a day in advance because Zoom links were sent out manually by me. So I needed a little bit of time to kind of send things out. But we actually have an automated process now. So the registration no longer closes a day in advance. It closes kind of at the start time of the seminar, and I might try to find a way to kind of push that back by 10 minutes just in case people are running a little bit late. So I'll work on that. And in theory, it should sort of automatically send you an email with an ICS file, which should be uploaded or uploadable to many types of operating systems and calendar applications. So hopefully nobody had any issues with that. But if you do have any issues with that, definitely let me know and I'll try to find a workaround for that. So let's get into it. I've got like a quick little intro for Nick, and then he can kind of dive right in. So today's talk is Neptune stratospheric composition, implications for internal and external processes. Dr. Nick Teanby received his PhD from Leeds University studying the Earth's magnetic field, and then switched gears slightly to seismology during his postdoc position. Seismology on Mars is in fact still an active study of research for Dr. Teanby, which is really cool. He joined Bristol University as a Science and Technology Facilities Council Advanced Research Fellow in 2010, and is currently a reader in the School of Earth Sciences and Geophysics at the University of Bristol. Much of his research now is focused on Titan's atmosphere, but he also has done considerable work investigating the atmospheres of Saturn, Jupiter, Uranus, and Neptune, as well as Mars. And so Neptune's atmosphere specifically is what we'll be talking about today. So thank you so much for joining us, and feel free to go ahead. Folks, if you have questions, you can drop them in the chat. You can wait for sort of a Q&A period afterwards. It's pretty informal seminar series, and so feel free to unmute yourself and ask questions if you'd like. So I'm going to turn my camera off just so that in the recording people aren't focusing on me, they're focusing on you. But yeah, so feel free to go ahead and get started. Nick, thanks so much.
All right, sounds good. Thanks for having us, and thanks for the intro. So yeah, I want to talk today about Neptune's stratosphere and what we can actually tell about the inside of Neptune from that, which sounds a bit odd, but hopefully I can persuade you that it's not a crazy idea. Oops. Let's have a click. So just kind of initially, why do we want to know about Neptune and what it's made of? Well, if we're thinking about formation of the solar system, it actually matters quite a lot what these ice giants are made of. Are they mostly rock? Are they mostly ice? And that has implications for formation of the solar system. So it would be good to know that, as well as for knowing more about the planets themselves. So this is a very kind of basic summary of the current model of Neptune's interior. So currently the favored model is an ice giant, where you've got an upper atmosphere with hydrogen, helium, and so methane and so on. You've got a mantle of mostly water ice and methane ice and ammonia. It's quite big. And then you've got a small rocky core made of silicates and things like that. So that's kind of the current ice giant model. So how did we arrive at that? Well, we do have some observed geophysical parameters. So Voyager 2 went past Neptune in '89 and measured various things, and we've had a few observations since from occultations and things like that. But we have an idea of its mass, and its radius, so we can figure out its mean density, which is, I think, around 1.5, something like that. We've got a few measurements of the gravity field, so the gravity moments. The error bars on those are quite large, but we do have them. We've got some oblateness, so we can tell Neptune is slightly squashed, and that tells us something about its shape and gravity field also. We think we know something about its rotation period, so we've got the rotation period of the magnetic field, but there's also rotation periods that can be derived from the winds in the stratosphere. So there's kind of a bit of disagreement on the rotation period, but we kind of know it to within about an hour or so. It's quite depending on the assumptions. We can infer some moment of inertia, and we know there's a magnetic field. So if there's a magnetic field, that suggests there's some conductor of some kind in the interior. So those are the geophysical things. So there's two main types of model that we can use to fit those. Model 1, which I've described here, is the ice giant model. So just sort of mentioned in that cross section, but there's also the possibility of a rock giant, which is a little bit fringe at the minute. So I'll kind of dig more into that later in the talk. But that's got an outer gas envelope as in the ice giant model, but then the interior is basically silicates mixed with hydrogen, helium, and some ices. So those two models can fit the data. So there's actually quite a lot of heavy elements in Neptune, probably between 75 and 90%. So there's quite, it's not a Jupiter-like body that's quite a lot of hydrogen, helium. There's quite a lot of other stuff in Neptune that's quite, makes it a bit more interesting. Well, I think anyway. So you can model the internal structure. You can try and fit these geophysical parameters, and this graph here from this recent paper kind of shows so the pinkish area gives you like the range of models, and you can see it's actually fairly well constrained on the outside, but as you get deep into the interior of Neptune, basically anything goes, and you can fit any old internal model to that data. It's a bit of an exaggeration, but a lot of different models will fit it. So it's not actually well constrained. And there's a nice review by Ravit Hellert in 2020 that covers these things quite nicely. So just as an example, I've overlain here two interior models from quite an early study from 95 from Podolak et al. Model 1, which is the blue one, is 90% water, providing the heavy elements, and model 2 is 75% rock, providing the heavy elements. So those are two really different compositions, and they result in these kind of profiles here. And both of those actually fit the geophysical constraints quite nicely. So the problem we have here in determining between these two types of composition is rock and hydrogen helium mixtures have quite a similar density to ice mixtures. So it's actually quite difficult to tell those apart just from mean densities and things like that. So is Neptune, is it a rock giant or is it an ice giant? It's unclear, I would say, from this, but ice giants are currently preferred. So that's it for the geophysics, but do we actually know anything else? So I'm going to spend the rest of this talk on the atmosphere. So the atmosphere is basically the top few hundred kilometers. That's the visible atmosphere. So if we can measure things about that, perhaps we can extrapolate to the interior. You know, this wouldn't really work super well for the Earth, I'd have to say. But for Neptune, there's a bit more of a direct connection between the interior and the atmosphere. So we can give it a go and see if we can come up with anything sensible. So not everybody, I guess, on this telecon is an atmospheric scientist. So just sort of review what a stratosphere and a troposphere are briefly. So it's kind of this very outermost layer of this cross section here. This thick grey line is the temperature profile measured by Voyager. So it was a radio occultation. And I've split this into two basic regions. One is the troposphere, which is the convecting region of the atmosphere. So that's like the Earth's troposphere, where all the weather happens and the circulation and so on. And above that, we've got a stratosphere that's stably stratified. So we've got hot stuff on top of cold stuff, and that tends to be quite stable. Whereas in the troposphere, this kind of profile can be unstable and you can get rapid mixing. So the stratosphere, what we can have is interplanetary dust particles entering this. We can have comets impacting the planet, and we can have emissions from moons. So say something like Enceladus on Saturn, if there's any geyser activity or anything like that, that could inject stuff into the atmosphere. Particles from rain, ring rain, so like bits of kind of dust and things like that falling off Neptune's rings could also be a possibility. In the troposphere, we've got mixing from the deep interior. So we could actually dredge stuff up from the inside of the planet and sort of get some of that mixed into the atmosphere, and we may be able to observe that. And then the interface here is the tropopause, that interface between those two things, where we don't really know what's happening, but do we ever, I suppose. So just pause for a few questions. So if we can observe the stratosphere and the troposphere, what does that actually tell us about the deep interior? Can we tell anything about the deep interior composition? Can we infer anything about the formation of Neptune? And as well, can we tell anything about the external fluxes? Can we see, okay, have we got any comets impacting into the planet recently? What kind of background of interplanetary dust particles are hitting the top of the atmosphere? So we can constrain some of these things by making observations of the composition and chemistry. So I'm going to focus on a few things. So these are a few things I'm going to focus on in the next few slides. The first one is temperature. So that has implications for the energy balance on the planet. So how much energy is coming in and out. And that in turn has implications for how vigorous the mixing is in Neptune's interior. We've got the carbon to hydrogen ratio. We can have an idea of that from measuring the methane abundance, if we can measure the deep methane abundance. And that's indicative of bulk composition and hence formation. Same thing with the D to H ratio. That could tell us what level of enriched ices have entered Neptune in the past, and what kind of abundance those things have in the planet. We've got carbon monoxide that's been observed quite a lot recently, and that has two possible sources. One is from comet impacts, which can create CO in the upper stratosphere. And the other is we can actually mix it from the deep interior. So that's quite an interesting one. There's carbon monosulfide, so CS, which is produced in cometary impacts. So that's a good indicator of comet impacts. I'm not going to say much about it here, but we can also measure the water vapor, and that's a good indicator of any background interplanetary dust particles that are getting into the top of the stratosphere. So temperature, so we measured temperature with the Voyager radio occultation back in the 80s, which is this nice grey line here, nicely smoothed, so all the wiggles have been removed. So that tells us something about the mixing processes in Neptune's atmosphere. In the stratosphere, if we've observed hydrocarbons, so things like ethane, for example, have been measured in the stratosphere, and there's profiles of those. And we can reproduce those in photochemical models. And what those models show is that you need a very low mixing near the tropopause somewhere. If you don't have a very low mixing region in the atmosphere, basically you mix all that sort of lovely chemistry from the stratosphere, you kind of mix it down into the deep atmosphere and it gets lost, and it's very difficult to maintain a significant abundance of hydrocarbons in the stratosphere. So we need this low mixing ratio here near the troposphere, near the tropopause, sorry. The troposphere, so deeper down here. So Neptune actually, as you probably know, is one of the planets that sort of emits like a lot more radiation that it receives from the sun. And we can use that to combine with a temperature profile and some scaling laws to infer a mix of sort of an eddy mixing parameter for the troposphere. And people have done that and get quite a high value of sort of 10 to the 8 centimeters squared per second. So this high heat emission implies very vigorous mixing in the troposphere. And for simplicity, that's usually just assumed to be constant throughout the troposphere. It's actually quite difficult to constrain that any more than that with the observations. So because of this very high mixing in the troposphere, that can give like a link between the upper troposphere, the middle troposphere, and the deep atmosphere. So we may dredge, that may be fast enough to dredge up some stuff from the interior for us to investigate. So methane. So methane is quite variable on Neptune. Just picked a recent paper here. There's probably 2 to 5% methane. Does vary significantly between equator and poles. But if you just take that bulk abundance of methane, that looks to be enriched by about 50 to 100 times the solar composition. I've took this nice plot here from a paper by Atreya et al. Also in 2020, and where we're plotting the abundance or the relative enrichment ratios of various species. And you can see basically that's all we have at the minute for Neptune, just this one data point from methane, whereas for Jupiter we've got a lot of things, and Saturn too, we've got a couple more bits of information for Saturn, but we're a bit limited. So just based on that, it would suggest about 50 to 100 times enrichment. So that makes sense. So we expect Neptune to have a lot of heavy elements, so it makes sense that it's enriched in those elements compared to the solar composition. So what about the D to H ratio? So that has been measured spectroscopically to be about 4 times 10 to the 5. That's with the ISO Space Telescope. We can assume that that deuterium is from water in the ice, in the planetary ices that form these planetesimals that form Neptune. If we can assume that, that's an obvious place for it to come from. The weird thing here is if we look at present day comets, the D to H ratio in those is actually quite a lot higher. So 15 to 60 times 10 to minus 5. So about 10 times more enriched than Neptune. So we have a bit of an issue here if we're trying to make an ice giant and 90% of it is these ices. And if those ices are anything like present day comets, then this D to H ratio doesn't make a whole lot of sense. So what we can do is we can, okay, take this D to H ratio. If we assume that the ices that form Neptune were like the present day comets, we can work out how much ice we might have in Neptune. And if you do that with this sort of very basic theory here, we get something less than about 15%. So we don't get a lot of ice. We do get some ice, but definitely not 90% ice. So of course, this assumes that all these ices are really nicely mixed in the interior and everything's homogeneous and it's all reached equilibrium, which we're not sure is the case or not. So it is possible that as you go deeper into Neptune's atmosphere, D could be more enriched. That is possible, in which case we could use these ices. But if we just take a very simple assumption and go, let's evenly mix the planet, then these two things seem to be slightly incompatible in the case of an ice giant. So that, to me, suggests like a rock giant is a bit more likely based on this evidence. that would suggest an oxygen enrichment of about 30 to 130 times solar, which is consistent with the methane thing. So I've done a little smiley face there. So that's all good. That's all happy. So right, let's get to something a little bit more weird. So carbon monoxide. So if you look at this top plot here, you can see this is a feature of carbon monoxide. We've got the brightness temperature here of the 230 gigahertz line. We've got an emission core, which is sensitive to the stratospheric abundance. We've got these very deep sort of absorption wings there, and they're controlled by the abundance of CO in the upper troposphere. So there's actually a ton of CO on Neptune. There's sort of 1,000 parts per billion, which is a lot. That's more than any other planet in the solar system by quite some way. I guess the most comparable planet is Uranus, which has only got 8 parts per billion in the stratosphere. So something odd is going on there at Neptune. As well, in the troposphere on Neptune, we've also seemed to have a lot of CO, maybe 100 parts per billion, which is also a lot. Whereas on Uranus, it's not even detectable. It's less than 2 parts per billion. So we kind of get a profile like this. So we've got high abundance in the stratosphere, low abundance in the troposphere. So for that kind of a profile, that suggests we have an external source, at least for the stratosphere. So for the stratosphere, this proposed source is just a large comet impact combined with shock chemistry. So what can happen on Neptune, because there's methane actually to quite high altitude in Neptune's atmosphere. If you get a comet entering the atmosphere, it's a very energetic process. There's a lot of heat created. What can happen is the water in the comet can react with the carbon in the methane, Neptune's stratosphere, and that can kind of create a lot of CO. So a lot of that stuff that would have been water ends up being in CO. We need quite a big comet to sort of explain this massive abundance. So is there any other evidence for this comet? This is like classic planetary science. Anything weird you can never understand. It's always some giant impact that's to blame. So, so is it actually, how like reliable is this massive comet? So we can look for other species. So Marino et al. Did this and look for this carbon monosulfide, this CS, which is also only really produced by shock chemistry in sort of high temperature reactions. So that would also require some kind of comet impact. And they did detect this. It's quite a nice signature here. That was observed in the stratosphere, and you can do some modeling of that, and it suggests maybe there was a kilometer scale comet impact in the top of Neptune in the last 100 to 1,000 years. So that makes sense. So that's also consistent with Neptune's very high abundance of CO. So this is the reaction here. So at low temperatures, water and methane are preferred. So that would just be low energy interplanetary dust particles entering Neptune's stratosphere. It would remain as water. Whereas if it's a comet, the cometary ice then reacts with this methane and sort of converts to CO, and you get this CO. So the fact that we've got the fact that I can't spell consistent, that's good. So this CO and this CS are consistent. They both point towards a cometary source for the stratospheric CO. So that gets another smiley face. That makes sense. So we think we sort of understand the stratosphere in terms of CO, but what about the troposphere? So this is very weird. There's a lot of different kind of abundance measurements for CO in Neptune's troposphere. There's quite a wide range depending on the study and the telescope used and so on. But approximately there's about 0.1 parts per million. So a way to explain this is that this CO is actually dredged up from the deep interior of Neptune. You can't really have this kind of a scenario with this amount of CO in the deep troposphere just from a comet, especially when you get to high pressure, the absolute abundance is just too high. So it's this same reaction again. So CO is actually stable in the very deep interior, so above a few thousand Kelvin. As that gets mixed up into troposphere, though, it's going to sort of decompose into methane and water and not be CO anymore. But we do observe this CO. So how do we actually get this internal CO up to explain this tropospheric abundance? So one suggestion is that if this mixing is rapid enough that you can sort of get the CO into troposphere before it's got time to decompose, then you can sort of quench the reaction basically and have CO frozen in place, because as you go to lower temperatures, this reaction rate becomes less efficient. So you can basically freeze in the CO abundance if you can mix it up there fast enough. So Neptune's very vigorous convection combined with quite a lot of oxygen in the deep interior could account for this. So this has been modeled. So people have modeled this properly using sort of thermochemical models. So there's a few examples here. So what you can do is you can prescribe the mixing. So a study here from Cavalier et al. You can prescribe the eddy mixing coefficient in the troposphere. You can read off the tropospheric abundance. So this black line here is showing the 0.1 parts per million CO, and you can read off what kind of OH enrichment you need in the troposphere. And here's another study, slightly older, but getting similar results. So these studies and this modeling kind of suggests if you had about 400 times solar OH enrichment, you could get enough CO mixed into the troposphere to observe and explain these observations. So kind of summarize this with a happy face in that this would explain it, but also a sad face because this doesn't seem consistent with the C to H and the D to H observations. Those abundance variations are quite different. And this is actually quite a lot of oxygen that we'd need. So 400 times solar in the interior of Neptune means you've got to make it of 90% ice or so. So this is one of the main reasons this ice giant theory has kind of got a lot of traction recently. So let's try and sum up what those observations are saying so far. So CO, stratosphere, I think we can explain that with a large comet. That all seems fine, and the CS is consistent with that. The troposphere, to explain this 0.1 parts per million, we need rapid mixing of CO from the interior that gets quenched. In that case, thermochemical models imply a rather large enrichment of OH, which means we need about 90% ice in Neptune. So this is suggesting an ice giant if we just took that at face value. But if we look at the D to H and the C to H, well, the D to H, yeah, if we kind of mix in, if we got this ratio here, 4 times 10 to the minus 5, and we're supplying that D with ices in the form of planetesimals, and if those ices are comet-like or like anything that exists in the solar system today, we can't really include that much ice if we're mixing it, otherwise Neptune will become too D rich. So we either need these Neptunesimals, which is like a planetesimal, but something that makes Neptune. We need either those to be depleted in D to H relative to the modern icy solar system bodies like comets and so on, which seems unlikely. Or we need incomplete mixing in the interiors, which could be possible. So maybe the ices are not totally equilibrated in Neptune's interior. Or we need some odd formation scenario like forming Neptune on the CO ice line, for example, would be another way to get lots of CO into the deep atmosphere. So these are the kind of possibilities. We've either got an ice giant, but we need one of these three explanations to basically explain this discrepancy between the observations. So depleted planetesimals that are no longer present in the solar system. This always like seems dubious, this kind of thing to me. Like if you've got something that you're using as an explanation and there's no observable like remnant of it, that seems slightly strange. But that would explain it. Maybe they all got used up during Neptune's formation, or we could have incomplete mixing, which could be possible. That would also be quite strange though, because this D to H ratio on Neptune, Uranus actually has quite a similar D to H ratio. And those two planets are very different. They've got different densities, so different heat fluxes. So it would be odd if they were mixed to different kind of degrees, but had very similar D to H ratios. I think that would be quite an odd coincidence. Or Neptune falling on this ice line. So the other thing, which I think, the other theory, which I kind of prefer, is that instead of that, we've got like a rock giant. And in this case, this O to H enrichment is overestimated by an order of magnitude or so. So sort of questioning whether this is actually real. So can't really just get away with just saying that, because there is observations that need explaining. So is this extreme OH thing real? So we need to reconsider these CO observations. So we only really need this extreme OH if we're trying to explain this 0.1 parts per million tropospheric CO. That's the only, if that's throughout the troposphere, that's one of the only ways to explain that. So if we look at the CO emission lines, we've got these cores and we've got these wings here. This is a contribution function. So this particular line here is limited to about a bar's worth of pressure. So we don't actually get super deep in the planet with these observations. So one possibility is that perhaps there's CO in the upper troposphere, but it's not mixed throughout all the troposphere, and it's just kind of something that we're seeing in the very uppermost troposphere. If we go to some lower frequency lines, we do get a bit deeper. So we can so these are the contribution functions. So we get down to a few bar with this very deepest line here. This is the lowest frequency CO line at 115 gigahertz. So, you know, we do get a bit deeper, but these contribution functions depend on the profile that you assume for the CO in the first place. So there's a bit of a circular argument going on there. Also, if we're going to observe this is actually quite a challenging thing to observe. This is quite a wide frequency range for a sub-millimeter observation. So you have to kind of stitch multiple tunings of a telescope together to kind of get that in place. So it's actually quite a hard observation to look at these wings. And also there is a degeneracy between the CO contribution and the temperature. So it's a little bit strange. So I did have an attempt at this with Herschel. So the Spire instrument on Herschel is quite nice. It's quite a low resolution, but it does cover a very wide range, and you cover 9 of these CO bands, and you get the wings really nicely defined, and you've not got that pesky Earth's atmosphere in the way. So that's kind of nice. So what I did here was try to fit all 9 of these CO bands all together, all at the same time, in an attempt to better constrain this CO profile. So I did try these step profiles, and they do fit the data very well. So this is what people have used in the past for these other observations, and this is partially why we assume that CO is going throughout the troposphere. But the interesting thing is that you can also fit these observations with these kind of gradient profiles that actually don't have any CO below about 1 bar. So they also fit the data very well. So all of these profiles that are plotted here actually fit those observations almost indistinguishably well. So there's some definite degeneracy here in the what the data is telling us. So perhaps CO is just in the upper troposphere, and if it's just in the upper troposphere, maybe it can just be from this comet, and maybe it's just filtered down into the upper troposphere, and maybe we don't need this massive enrichment. So I did a little bit of a test here just to try and quantify this. So tried a bit of a sensitivity test. So I took this black profile here as, so if you say that is the actual carbon monoxide profile on Neptune, generate a synthetic spectra, add some noise to it, and then try and fit it, but try and fit it with this step profile. Can you actually fit it? Or this kind of a profile here, this gradient profile, but with some deep abundance. So if you do that, you can actually fit this very, very nicely with any of these profiles. So you can almost, the step profile is slightly worse, but only slightly. So it's actually really difficult to constrain this deep CO abundance with, even with a really nice synthetic observation like this. So another thing is you can get an even better fit if you just allow the temperature profile to just adjust itself by a few Kelvin. You can actually fit this step profile almost indistinguishable from the data. So fits the data perfectly well, but it's also wrong. So it's you got to kind of watch these parameterized profiles a bit, kind of bit tricky. So can't really take them too literally. Maybe there's some deep abundance, maybe there isn't, but I think with the data we have, it's not really possible to probe much below about 1 bar. So we can say there's CO above at pressures of a bar or less, but I think below that is, at higher pressures, it's actually getting quite difficult to pin it down. And this kind of explains this massive variation in published CO results. So this is just a few of the more recent studies. So the stratosphere, you know, there's a factor of 2 difference in the stratosphere, which is not too bad for planetary science. That's kind of fine. But you get down into the troposphere and it's basically anything goes. You can have anything from 0 to kind of sort of half a part per million, even quite high abundances. So this degeneracy and sort of lack of sensitivity could explain this variation in the previous results. So if that's getting put forward as a explanation, and I'm saying there's not a lot of CO in the deep troposphere, does that cause any issues? Well, it causes one issue. If we're having this mixing profile, which is the usual mixing profile, we've got sort of rapid mixing throughout the troposphere. And if we have that, we're not going to be able to maintain any significant CO abundance in the upper troposphere if it's only sourced from an ancient comet. Because as soon as it gets into the troposphere, it's going to be mixed down and diluted into the deep atmosphere, and we're not going to see any significant amount. So this proposal of CO just in the upper troposphere isn't really consistent with this eddy mixing profile. But what if we shuffled this down a little bit and use this dotted blue profile instead, which is consistent with some photochemical modeling? Then that would actually sort us out, because then we've got very low mixing in the upper troposphere and we can maintain that CO there. So this would mean this part of the atmosphere is a bit more stable. So that could solve our issue, but we do need to modify the mixing profile if we're going to go for this as an explanation. So you can look at a temperature profile. So the temperature profile is not massively well constrained. We do have this one. So well, we've got an ingress and egress on the Voyager radio occultation and a few other bits of info. So we don't know that temperature profile massively well, but if we plot the lapse rate in this panel C here, we can use some sort of basic atmospheric theory where if the lapse rate is less than the adiabatic lapse rate, then that indicates the profile should be slightly more stable. So this stratosphere is all stable. It looks from this temperature profile that down to about a bar is perhaps a bit more stable than below that, where we kind of start to get less stability. Another slight bit of evidence is if we look at the brightness temperature at sort of deep in the infrared, the brightness temperature of Neptune is about 60K. So if we read off 60K on this graph, it's sort of around about half a bar to a bar pressure. So that suggests the sort of radiative convective boundary is around about 1 bar-ish as well. So this is all sort of pointing towards less mixing and in the upper troposphere there. So I think this could all be vaguely consistent. So I'm going to twist everybody's mind with this terrible plot that was me trying to put all this info into some kind of flow chart and figure out what implies what. Because there's a lot of bits of information about Neptune's stratosphere and troposphere, and what they actually mean depends on what you assume what's going in. So there's a few things here. So these things in orange are things that we don't really know. So we don't know the composition of the things that formed Neptune. We could assume that they're basically like modern day material, but they could be different. We don't know how well mixed the interior of Neptune is. Is it equilibrated or not? And we don't really know the CO profile. Is there CO throughout the troposphere, in which case we need an ice giant, or is it only in the upper troposphere, in which case we could explain it with a rock giant? So I won't dwell on this. I suggest you go to this paper if you want to, dig into this plot anymore. But basically, there's a lot of bits of information. Not all of it is consistent. It can only be made consistent by assuming various things. So we basically need some more observations of Neptune. So the final slide now, just to summarize what I've been rattling on about for the last 35 mins. So we do have some geophysical observations, but they can be fitted with almost any composition. So the M members of ice giants or rock giants, all of that fits the available geophysical data. The carbon and deuterium enrichment suggest about 50 to 100 times solar enrichment, whereas if there is any tropospheric CO, that suggests OH enrichment about 400 times solar, which is not really consistent. So to explain this CO is a bit problematic. So one is an internal source, which is mixed from the deep interior, which I think could potentially be an overinterpretation of a step parameterized profile, because I don't think that accurately represents the CO profile in Neptune. And I think we're actually limited to only information sort of a bar pressure or less, in which case I think all of that CO is basically confined to the upper troposphere, and it could also be from the comet. So a possibility for a self-consistent interpretation of all this various info is that we have a rock-rich Neptune, but with some ices. The planetesimals that form Neptune are similar to sort of present-day comets and have a similar D to H ratio. That would be nice and neat. Maybe these pre-Neptune planetesimals, seems unlikely that they're all ice. That also seems odd, but we have things like Pluto and icy moons and Kuiper belt objects and all this kind of stuff, and most of those seem to be about 70% rock, with the rest being ice. So we could have that kind of a composition if we have a rock giant, and then in that case the OH enrichment would come down a little and be more in line with the C and the D. So I think that's all pointing towards a rock giant with some ice instead of just an ice giant with 90% ice. I think we do need more information to check if this is actually the case. So ideally, an entry probe into Neptune would be cool, going down to 10 bar, measure the temperature profile, measure the mix-in, measure the CO abundance. That would be really useful. Not sure how long we'll need to wait for that, but that would be awesome. And just finally, if you want to see any more detail about this and have a more coherent explanation, it's all wrote up in this paper. And there's a really nice special issue actually on the ice giants and Neptune, and it's part of that issue. And I really recommend you check it out because there's some really nice review papers in there. Cool. And that's me done. Thank you very much.
Awesome. Thank you so much. That was such an incredible talk. I love the flow chart, that kind of flow diagram.
Oh, yeah.
It really helps like map things out in my mind. It was really incredible.
Yeah, I never thought I'd do a flow chart. At some point you have to do one to try and figure out how all this stuff pieces together.
Definitely. It helps visualize it for sure. So yeah, so folks can do the raise hand, you can unmute, you can post your question in the chat if you'd like, anything that you'd like to do. I see that Cyril has their hand up, so yeah, go for it. Go ahead and unmute yourself. Oh, the hand is up.
Thank you so much for this comprehensive overview. I got a question about your suggestion that a comet impact about 100 or 1,000 years ago can explain the CS abundance in the stratosphere. So I have a question concerning that, because if you wanted to come up with this estimate, it seems to me like there would be a degeneracy between the mass of the comet and the age, because if you have a more massive comet which struck the stratosphere a longer time ago, then more CS would be broken down into methane and hydrogen sulfide. So how do you break this degeneracy between the amount of water introduced and the age of the impact?
I mean, that wasn't modeling that I'd done, but I think the study by Marino covers that really nicely, where it's as you say, it's actually quite difficult. So if you've got a comet that's too big, you kind of don't deposit it in the stratosphere. It can kind of make it through into the planet. If you've got a comet that's too small, the temperatures are not hot enough during the impact to do the shock chemistry. And also the bigger comet becomes less and less likely. So it's a combination of things. You need, I did briefly look at the impact rates, and yeah, I think it is about 1,000-ish years for a kilometer scale impact into a planet sort of at Neptune's location. It should be possible. And as well, the shock chemistry stuff is actually not super well constrained either. So there's all these things. So this is why it's like a few hundred to a few thousand years, and kilometer scale, it's a bit like it's a little bit hard. It's a little bit hard to pin down, because like all of those observations are like the CS observations really nice and precise, but interpreting it's actually quite difficult. So.
I see. Yeah, thanks a lot for the explanation. Makes a lot of sense.
No problems.
All right, then I think I saw Rick's hand go up. So yeah, go ahead.
Hey, Nick, nice talk.
All right,
I was wondering, from the geology standpoint and, thinking about Triton and infall, is there anything that you think we could observe in the upper atmosphere that might hint or contaminate you in some way that we don't know yet? Or what would you look for to try to find maybe some interconnection between Triton's geysers and maybe the stratosphere and all of this?
Yeah, interesting. You need some weird compound. If it's, yeah, you need something that you couldn't easily get from a comet, perhaps. Maybe some of the, thinking of Enceladus, I think that had some salt in the plumes maybe. I wonder if there's any those kind of compounds, because like halides, for example, you can sort of those have got quite nice emission features, but we've not found those on any giant planet really. So those are not really visible because they get kind of scavenged quite quickly in the atmosphere. So yeah, that's a good question. I'm not really sure what the smoking bullet would be.
Future proposals, right?
Definitely. There's an interesting thing on Enceladus where there's a whole like torus of like water vapor and things that you can observe, and you can even see like Saturn through the torus, and you can see the absorption of the water vapor and so on. So maybe something like that, and then you could sort of model it. But maybe one thing could be looking at the distribution, like the spatial distribution on the planet. So if we say maps the water abundance in the stratosphere, it might be concentrated, say, towards the equator if it's coming from the equatorial plane, whereas if it's just sort of dust particles with quite a generic source, we'd expect that to be quite even. So maybe something in the distribution of the sort of stratospheric water vapor would be good for that. Could be interesting.
Cool, thank you.
Cool.
All right, I think, so there's a couple of hands raised, but I do want to make sure questions in the chat are also acknowledged. So I'll quickly read one in the chat and then switch back to hands. So there's a question that asks, how might a rock giant instead of an ice giant composition change the interpretations of Neptune's energy balance?
Tricky. Yeah, another good question to ponder. I mean, we still need to explain the energy output, and we still need some vigorous mixing from the interior, but I'm not really sure anybody really understands that anyway. So it's quite. So yeah, I'm not sure how that would change things.
Like Rick said, maybe a future proposal.
Definitely.
Figure it out.
Yeah, we need more research, I think, definitely.
Okay, yeah, Mark, if you'd be willing to unmute.
Sure. Hey, Nick, good to see you.
Hey.
I just had a question about your Herschel retrievals. When I was looking at the plot of all your fits, it looked like one wavelength was fit much more poorly than the others. And I wondered if that was pointing you towards a region in the atmosphere where, that's where our assumptions about the vertical profile are falling apart or something like that.
Let's go back to that.
Yeah, I thought it was by eye anyway. I thought panel D, David.
Yeah, that is, so that one, so you can sort of see the deeper one, so like A at long wavelength, you're mostly sensitive to the wings, so you're mostly sensitive to the deep abundance, and then the higher frequencies, you're mostly sensitive to the stratospheric abundance. So this part here, this D, I think you're kind of in that boundary. So I think it really matters what you kind of do to the profile in that region as to how good a fit you get there. So you can fit that with like a bit of a crazy profile, but I kind of, I wasn't convinced enough to, you need like wiggles all over the place basically. So yeah, I think that we'll try to fit these 9 data with basically quite a simple profile. So yeah, it's that simple profile is probably not totally appropriate. So I think, there's probably something in that boundary region that is causing that misfit. So maybe a slight, I've just got a very basic linear gradient going on there, which is probably a bit too simplistic. So it could be kind of more of a curved thing or something like that, perhaps. As well, some of this data this Spire data does have like slight rippling on it that you need to correct for. So I'm a bit wary of trying to overfit this stuff because it's kind of you end up sort of fitting like weird artifacts and so on. Like this C, for example, I'm not totally sure that this baseline is entirely reasonable there. So yeah, I think that there's something in that region, upper troposphere region, is probably more complex structure than I've got. But yes, it's a good point. Thanks.
Okay, thank you.
No problems.
And then I think Gordon had their hand up, so feel free to unmute.
Hello, Nick. Great talk.
Cheers,
yeah,
Gordon.
Yeah, I've been interested in this sort of conundrum of what the C to H ratio seems to be telling you one thing, but the D to H ratio is telling you something very different. I guess coming from Jupiter and Saturn background, kind of think there should be a common enrichment factor for carbon, nitrogen, oxygen, phosphorus, and that seems to be the case for Jupiter and Saturn. But when you get out to Neptune, it doesn't really seem to make sense. The DH really stands out as something that's kind of weird. That how can you have a 50-fold or 100-fold enrichment in carbon and such a small enrichment in deuterium? And so, yeah, I mean, you mentioned it could be a rock giant, but then that kind of goes against our ideas that the magnetosphere of Neptune is, has this liquid metallic hydrogen rolling around. And would a rock giant do that? Anyway, it just seems like there's a lot of contradictions.
That is one issue with the rock giant, is you got to still make the magnetic field. So with the ice giant, that's quite easy because you've got sort of superionic water, which is conductive, which can do that. With the rock giant, I think some of the knowledge is not there. We don't know if these mixtures are conductive enough to generate a magnetic field. There's been some very recent work that I just saw where there's been some experiments looking at silicate hydrogen helium mixtures, and I think they did find some evidence for it being quite conductive. So that's encouraging that maybe it's possible. So they could be conductive, or I could imagine like there's some ice content and maybe there's an ice rich layer that provides some mechanism to make a dynamo of some kind. But the magnetic fields on Neptune and Uranus are pretty weird. They're not sort of nice dipolar things like you've got at Jupiter and Saturn. It's kind of all kind of crazy structures and things, which I think suggests the field is probably generated quite shallow in the planet, not kind of right in the deep interior. But yeah, it's definitely a good point. Yeah. So I think that, yeah, some more lab data on that would be really helpful, I think, to answer some of those questions.
And as an observer, I'm always interested in getting new data. So I'm advocating on future missions that we measure the HD line at high spectra resolution, because maybe that, things will change because with the high spectra resolution, you can get a stratospheric emission line and a tropospheric core. And I think that should help. It may just verify the Herschel results, but it might give you something new.
Yeah, I think that'd be really helpful to try and, because say we just measured a generic CO abundance on Neptune, that wouldn't really be very helpful. So it would be nice to get a bit more res on that D2H and maybe see if there's any variation with altitude. I think that'd be really nice to see if that's possible. That'd be cool.
All right, thanks, Nick.
Cheers.
All right, well, it's a couple minutes past the hour, so we should probably wrap it up. But if you have any more questions for Nick, I'm sure you can email me and I can put you in touch with him. You can email him directly. And we usually do sort of like this community news part at the end of the at the end of the seminar series. But since it's already a little bit late, we'll skip it this time. But feel free to reach out to me if you're interested to see what the community news are. But other than that, thank you so much, Nick, for this incredible talk. Thank you to the audience for some incredible discussion. And the recording will be up on the website within maybe a week or so. And please register for future events. I'll put the link into the chat. The next one is going to be Jason Hofgartner talking about Triton's plumes, and so that might maybe that might be a good time to sort of pair up what Rick was suggesting about Triton's plumes and Neptune's upper atmosphere. That might be kind of interesting. So. So I'll sort of leave it at that. Thank you all so much for coming. I'll stop the recording now.